So today's lesson is covering the speed of sound. The speed of sound. So just to recap from yesterday, we did not talk at all. By the way, yesterday I did not talk at all about the speed of sound. I talk about the amplitude of sound. So remember, that's the loudness. If I'm talking very quietly or very loud, and then I talk about the frequency of sound, which is either you're talking at a very low pitch, which means your voice is very deep, not low, deep. Sorry, not quiet, deep, like an opera singer, a male opera singer, or a high pitch, like someone basically, screaming at a very high pitch, or even like, just buzzing like a fly at a very high pitch sound, or a high pitch frequency, I should say. Okay, those are the only two things we covered yesterday as for sound nature. And then we talked about the sound intensity, which is related to the volume or the amplitude of the sound. So today we talk about the speed of sound, the speed of sound. So the speed of sound is just like the speed of absolutely anything else. Okay, so this is slightly going to relate to kinematics from unit 1. So the speed of sound is just basically how fast does speed travel, or in other words, how much of a distance does the sound wave, like it's like a water wave, but a sound wave, travel in a certain amount of time. Okay, it's literally just speed over time. Okay, so for example, if you stand at one point and you are the sound source and you scream, and someone else is standing very far away from you and they have a stopwatch, the moment the moment they hear you scream, from the moment you actually made or produced the scream, is basically the time it took for the sound to travel from you, the sound source, to your friend, the sound receiver or the sound detector. Okay, I'm just going to go back and forth between the screen and the chat just to check if anyone has any questions. Okay, so for first question is, what things or what factors does the speed of sound in any medium? Remember, sound does not travel in nothing, in space, in vacuum. It needs, let me just choose the color. It needs a medium, which could be a gas, or it could be a liquid or a solid. So this is sound, this is liquid wave, and this could be shock waves or ground waves or whatever. Okay, so it depends on many factors. Probably the easiest three to think about are, number one, since it depends on the medium, as a gas or a liquid or a solid, that means it depends on the what? It depends on the density or the packing of the molecules or particles. Okay, if you have a dense medium, it will travel in a differently than it travels in a less dense medium. So the density is important, and even the density between a single state medium, like between different gases themselves, actually what affect the sound speed as well. Okay, so that's the first thing. Second thing is temperature. How much are the particles vibrating? Okay, if they're vibrating more, that means they're bumping each other, or the scientific term is colliding with each other more than before. So that means the sound will travel differently if it's a very low temperature, or if basically the particles are not having a high rate of collisions with each other. Okay, so density is important, temperature is important, and finally, kind of related to density, I guess, but it could be a different factor all by itself, which is basically the material itself. Okay, I'll repeat again. So the speed of sound again depends on three main factors: density, which is the packing, so how close the particles are together. Number two, temperature, how much the particles are vibrating, and number three is the material or the bond structure of the particles themselves, which you could argue it's related to the density. It is, but again, you could have the same material more dense or less dense. We all know that you could make liquid. You could liquefy gases by putting them under extreme pressures, like liquid nitrogen. Nitrogen in room temperature is a gas. It's a perfect gas naturally. That's the way it's actually bonded together. But if you actually lower the temperature and increase the pressure, you're basically compressing it together, and it could actually liquefy at, I believe, the liquefaction temperature of liquid nitrogen is about, I think, in the minus 45 degrees Celsius. So it's under sub-zero. Obviously, it has to be sub-zero. Okay. Also, there's another factor, which is pressure. So, but pressure again is related to what? The more you go up above the sea level, the more you go above the sea level, you know that you have less pressure because it becomes harder to breathe. Okay, all the gases basically have lower density as you go up in the air. But that's again related to what? Related to density and temperature. So we're not going to talk about pressure much. Okay. If you become an atmospheric physicist, or if you become, for example, some kind of a person who actually studies, high altitude breathing and so on, then it becomes a very important factor. Okay. All right. Let me check. All right, we're good. So in air near sea level, okay, so ground level, I guess, the speed of sound has been measured and was found to mainly depend on the temperature of the air. The temperature of the air. And the easy way to remember it is at higher temperatures, so in hot weather, okay, sound travels very fast. Sound travels very fast. And in lower temperature, sound travels much slower. Okay. And the main reason for that is because temperature affects the what? As you remember, we said it affects the vibration strength. The more collisions you have between the particles, that means what? The more probability they will actually have at transferring the energy between the air layers. And that's why basically it travels at a faster rate. They found out that when the temperature is low, the opposite happens, and it still travels, but it takes longer time for the energy to go in the air or through the air all the way until the what? Until it reaches your eardrum or the receiver or the detector or whatever you want to call it. Okay, so the main thing we're going to be talking about today is the temperature dependence on, sorry, the sound speed dependence on temperature. Okay, so that being out of the way, the only equation that we need to worry about for this part of the lesson is basically this. Okay, so the mathematical formula that relates two things, only two things: the speed of sound in air to the temperature of that region of air is basically this equation right here. This equation right here. Now you might ask, where did this number 331.4 or those numbers 331.4 and 0.606 come from? Those are what we call experimental or empirical numbers or values. So basically, those are not from theory. No one came up with a theory to actually come up with those numbers. They basically did this. So let me just give you an example. They measured the speed of sound. And then they measured the temperature. And then all they did was they plotted temperature or graphed temperature and what? Speed of sound. So I guess VS, V for speed, S for sound. Okay. And then they found out that the temperature was getting higher. So they made the temperature go up, increase step by step. And for every single increase of temperature, they measured the what? They measured the speed of sound. And they basically found out that the dots or the experimental values kind of look like this. Okay. Some of you might have heard of something called curve fitting or the line of best fit. So they were like, okay, those points seem to be following a straight line. The question now is, how do we use? And by the way, Microsoft Excel has a feature that does this in a microsecond. It basically gives you the best line of fit, or the line that basically does two things: has the slope you need, that goes through most of the points or between most of the points. So they basically extended it, and then that was basically the equation that they actually came up with. So they actually purely did it by line of best fit. So the first number, everyone, this number right here, this is basically what we call the y-intercept, or basically this right here. Sorry, without this. Yeah, there we go. So this right here, this value right here is 331.4. And this number, 0.606, that would be the what? That would be obviously from math, 331 is the y-intercept, which means there's only one possible option for this one. This has to be the slope of the line. Remember, y equals mx plus b, but they actually wrote it as y equals b plus mx. That's, again, it's both of the equations are correct. Both of the equations are still correct. So they just chose this form right here. It doesn't really matter. So this becomes the y-intercept, and this becomes the slope. Okay, so the slope of the line, or basically rise over run, if you remember that from grade 10 and 11, rise over run, the ratio between rise and run, they actually found out that rise over run of this line, rise over run of this line gives the ratio point, or the decimal 0.606. Okay, that's basically it. Imagine this very simple equation was basically figured out using grade 9/10 math. Okay, so basically Vs, so the equation is Vs equals 331.4 plus 0.606 times T being what temperature. An important thing here is to realize, one second, let me just drag this here. There we go. An important thing to realize here is this is a physics equation, which means, number one, the temperature has got to be measured in Celsius, which we've been doing since the heat transfer part of the energy and work unit. So far we're used to that. You have to measure it in Celsius. This number here is actually this speed of sound. So it has to be measured in meters per second. And this also is the speed of sound as well. So you might ask, just hold on for a second. You might ask right now, how come I have two speeds of sound, or two speeds in the equation? This speed of sound right here, this speed of sound right here, this one, 331.4, is actually called the zero temperature speed. Zero temperature speed. And it makes sense from math for one reason, is because the y-intercept, which we already said this is the y-intercept. Let me go back to the graph. The y-intercept is always known to be what? The value of the function when you hit zero. So basically the value when you hit zero right here, zero. And this is, since this is temperature in Celsius, this would be 0 Celsius. That's why this is called the what? The zero temperature speed, or 0 Celsius speed. Okay, so we already know that without doing anything to the equation, this the speed of sound at temperature 0 at sea level is 331.4 meters per second. Okay, which makes sense because everyone, look, if you make this number 0, if you make this t 0, that means what? This whole thing goes away, and you indeed get what? You indeed get the 331.4. Okay, so whether you actually look at the graph or the equation, it makes perfect sense. Okay, so I'm just going to go back so to have it cleaned up like this. Okay, so always remember, this is the equation that we just need to work with for the next little while. 331.4 plus 0.606t. By the way, you should also remember now that this means if your temperature is high, the 0.606 times t is also going to be high, which means you're going to be adding something to 331.4, which means the speed of sound is going to increase. Again, remember what we said. In high temperatures, this equation goes up. So this is an increasing behavior. Also, if the temperature is very low, even below zero, like minus 20 degrees, you know that 0.606 times t, 0.606 times t is going to be a negative number, which means you're going to be subtracting from 331.4. So always remember, 331.4 is the zero temperature. Anything above zero temperature, above 0 Celsius is going to have a higher speed than 331.4. Anything below 0 Celsius is going to have a speed below what? Below 331.4. So 331.4 is your speed at 0 Celsius. Bigger is bigger, smaller is smaller as well. Okay, so let's actually see how we can apply this equation. All right. Okay, so a very standard question here, straightforward, which actually means it's a forward problem and a backward problem. If the temperature of the air in your region is 32 degrees Celsius, what is the speed? What is the speed of sound in air at that temperature? So right then, you know that we have the equation Vs equals 331.4 plus 0.606 Now, instead of T, I could put this number. So it's 32, and you just have to make sure it's in degrees Celsius. I will never give it to you in Kelvin or Fahrenheit anyway. I'll just make your life simple. So all I have to do now is what? Obviously, BEDMAS says I need to handle this one first. So 331.4 plus, and we just have to what? Let me just put up my calculator right here. 0.606 times 32, which is 19,392. 19.392. Let me just quickly check attendance. Okay. And then all I have to do now is literally just add this number to 331.4, which is 350.792. 350.792. Now, according to our equation here, we have two sig figs. So this must be written to two sig figs. So obviously, this is closer to what? This is closer, if you round, this is closer to 351 meters per second. However, this is what? This is 3 sig figs, so it should be what? 350 meters per second. Okay, 350 meters per second. I am not sure why they kept it to 3 sig figs. Sometimes the book does not fully go with our rules for sig figs. Okay, so we will go with 2 sig figs, 2 sig figs. But that's basically how we apply this equation. Okay, all right. Let's do another equation. Sorry, I mean another problem. But now this problem is the reverse. So now they're giving you the what? The speed of sound. Sorry, the speed of sound in your region. So the speed of sound is 333 meters per second. So Vs is that. What is the ambient? By the way, ambient or ambience means just basically the surrounding temperature. Okay, remember, I'm not gonna use words like this in your assignments or quizzes or tests. But ambience just means, surrounding environment. So what's the temperature of the what do you call it, of the air? Okay, now you can do this in two ways. Okay, you can do this in two ways. The first way is to purely use numbers, or you can use the symbols, rearrange for T, solve for T basically, and then plug in the 333 in place of Vs. I'm gonna do that for today. Okay, I know that all of you can manipulate the numbers, but I want to give you more practice on seeing how you do the symbolic or the algebra without numbers first. So I'm gonna start with the equation. So Vs equals 331.4 plus 0.606 times T. Okay, can someone tell me what's the very first, only one single step? What's the one single step I have to do first if I want to solve for T? Yes, Leila, go ahead.
Subtract the 331.7
yes,
from the
absolutely. Awesome, thank you. So remember, everyone, Leila suggested to basically subtract this guy or move it to the other side. I know that some of you probably would do a double motion. Basically means what? Means move this whole thing here and then move this thing here. While that is 102 thumbs up correct, 100% correct. However, one bad thing happens here is that your coefficient of 0.606 becomes negative. So there's need to do that. Okay, remember, you've seen me so many times keep the variable on the right side. That's 100% okay, and it liberates you from being so fixated on doing it one way. So perfectly, as Layla said, we will take this right here and kick it here. So we will get Vs minus 331.4 equals 0.606 T. And then what's the last step to completely isolate for T? Come on. Yes, Layla?
Divide the whole thing by
exactly
0.6 something.
Key thing is to divide the whole thing, which means many people will only divide this. Many people will only divide this, or some people, I should say, but it actually should be the entire side with the entire side. So some people like to give themselves a visual like that. Oh, sorry, not T, the 0.606, my bad. You never divide by the variable. You divide by the number you don't want to see with the variable. And 0.606. So your final answer is T equals Vs minus 331.4, 0.606. And now you just invented a whole new equation, or I don't know if people remember grade 11, you've definitely covered something called inverse function, which is basically the function that instead of being input and you giving me output, I'm going to give you the output. You have to give me the input that made that output possible. So now we are ready to one shot this whole thing with the machine we just invented. T equals, and we plug in 333 minus 331.4, all dividing 0.606, sorry, 0.606. Remember, everyone, just as we said, the fact that your speed, just so you know, a logical check quick here, the fact that your speed is 333, which means it's bigger than 331.4, the base temperature, zero temperature speed, you know that your temperature is going to become positive. Remember, if your temperature is above zero, the speed is above 331.4. If your temperature is below zero, the speed is below 331.4. So even without answering this question, we know our speed has to be above zero. And it will end up being that, because 333 minus 331.4 is 1.6, 0.606. Look at those two positive numbers. You have got to get a positive answer. 1.6 divided by 0.606, which is 2.64. What's this sig fig situation? 3 SF. So we will keep it to 2.64 degrees Celsius, which is exactly what they got. Okay? So this is how we do the forward calculation, like this one, and the backward calculation like this one. Okay? All right. Any questions so far? So far, it seems like a math manipulation more than physics, which honestly it is. Up to now, I just gave you the equation, and now we're just playing with it. Okay? All right. Now let's do a more complex problem, because you definitely are thinking right now, there's no way that this equation or this type of situations could be just this easy. Can it ever be negative? Avery, are you talking about the temperature? 100%, absolutely. And the only reason that could happen, or the only way that could happen, is if your speed is going to be what? Less than 331.4. So for example, if the question, great question, if the question was instead of 333, it was, I don't know, 290 meters per second, you know that your temperature is going to have to be what? Your temperature is going to have to be quite negative for that very low speed to actually be realized. So yeah, so everyone, by the way, just a conceptual thing here. 290 meters per second is still so freaking fast. It's insane. I mean, remember the conversion between meters per second to kilometers per hour? The magic number is 3.6. So if you're in meters per second, just multiply it by 3.6 to see how fast it goes in kilometers per hour. So 290 times 3.6, sound traveling at 290 meters per second is equivalent to a car traveling at 1,044 kilometers per hour. It's still so fast according to us, but according to many other phenomena in nature, like light, it is unbelievably slow. Okay. However, the key thing from Avery's question is that if the speed is lower than 331.4, you know that your final temperature answer must be negative or below zero. How negative? I don't know. Obviously, the slower the speed, the more negative or the colder the temperature has to be. Okay, perfect. All right. So now let's do a very interesting problem that actually involves more than just applying one single equation here. Okay. So I want everyone to, well, I'm assuming everyone has pencils down and everyone's just like watching and hopefully letting things sink in. But let's just talk about this problem here. Okay. We will do it in complete detail, but let's just let the whole situation sink in. So while walking through the Grand Canyon, which is one of the hugest rock formations in North America, in the States. So it's basically like a geological, amusement park. So while walking through the Grand Canyon, so you're basically, it's basically full of huge, tall walls, basically. You scream right at a huge rock formation ahead of you. So you see a huge wall or an obstacle and you just scream, okay? You basically produce a sound. It's not just you, your friend there is there as well. your friend who is 20 meters behind you, 20 meters behind you. So you are in between your friend and the wall, or at the rock formation. Here's now, everyone listen. He does not, or she does not hear the original sound. They hear the echo. Echo is what? Echo is sound bouncing off something. Okay, you never produce echo in open space. You never produce echo in open space. Echo is basically sound bouncing off a certain obstacle, like a wall, something, or the walls in the hallway. Actually, if you stand near our classroom door and you scream, very quickly you can hear an echo, because obviously the sound is reverberating and bouncing off the walls. So here's the echo after zero point 0.7 seconds after you scream. Okay, it's a hot day in the Grand Canyon where the temperature is 35 degrees. Usually it's higher than that, but let's just go with 35 degrees. The question is just very simple. How far are you from the rock formation? How far are you from the rock formation? The only distance we know right now, everyone, the only distance we know right now is that your friend is 20 meters behind you. You have no idea how far you are from the rock formation ahead of you. Okay, definitely this needs what? This needs a diagram. Okay, well, here is a very basic diagram. Okay, so let's just look at this very slowly. So obviously we have two people and the rock formation. We know for a fact that this one right here, this is the friend. So, oops, sorry. So this is the friend. So this is friend. And the one in between, that is you. And that's the rock formation. Okay, so the sequence of events is basically this. You scream. So that means when you scream, you do not ever produce a sound in one direction. You actually produce sound in 360, all, not just two-dimensional, in three-dimensional. So you actually produce sound this way and this way and this way and this way and this way, behind you, above you, everywhere there is sound produced. But you know that the one we're caring about here, the wave we're caring about, is that the one that goes here. So I'll basically sketch it. Remember, this is usually how we sketch sound waves, because they are longitudinal, like basically a slinky. So you scream. By the way, your friend is going to hear you twice, everyone. Your friend first is going to hear this wave or this sound. Yeah, that's fine. But for whatever reason, we're not caring about this wave. We are not caring about this wave. I'm going to erase it. We care about the second time your friend is going to hear you, which is going to be when sound bounces off and goes all the way towards them. Okay? They hear that sound going from you to the rock back to them after 0.7 seconds. After 0.7 seconds. Obviously, a very short time, because first of all, they're not very far away from you. Second of all, sound does travel very fast compared to us. So that's why it takes very short time. That's why it takes a very short amount of time. Okay. All right. So let's put some numbers here. Well, whatever numbers we can fit, or we can actually figure out. Obviously, in somewhere in the air, I'm gonna put what? 35 degrees Celsius. 35 degrees Celsius. Done. Then we know that there's a 20 meters somewhere. Obviously, it's not here. That's not the 20 meters. Otherwise, there's no question to ask. We already then know how far you are from the rock formation. The 20 meters is right here. The 20 meters is the distance between you and your friend. Oh, and by the way, I just realized, I know that means things are going to be down to 1 sig fig. Don't worry, we're going to deal with that at the end, okay? We're going to make the sig figs higher. It's okay. So this is not 20. This is the X we're trying to find. This is the question mark we're trying to find, okay? So I'm hoping the diagram so far makes sense. So there's 20 meters behind you to your friend. There's 35 degrees Celsius. And we are asking about the X distance, or the question mark distance, between you forward to the what? To the rock formation. Okay. All right. Let me check. Okay. So far, so good. All right. So let's actually, okay. Now here's the thing. So this is a cleaner diagram. So I'm just going to add 20 meters here. And here's my 35 degrees. Now, You see, sorry, here. You see how I actually labeled the point 0.7. I basically wrote, or I made an arrow that basically goes in two trips, technically two trips. One trip from you, this is you, by the way, this is you. One trip from you to the rock formation, and this is this part. Everyone, this is this part right here, this part. And then another part from the rock formation all the way back to your friend. The 0.7 is both parts together. The 0.7 is both parts together. It's not just the 0.7 seconds from you to the rock or from the rock back to your friend. It's both of those times added together. Okay? All right. So the question now is someone asking a question? Okay. So the question now is, how do we actually find out the distance between you and the rock formation? Okay, I'll give you the easiest way to figure out values in this problem. Number one, everyone, number one, do we have the temperature? Do we have the temperature in this situation? The answer obviously is yes. Right there, immediately, you have the temperature. At least you can get some marks by finding the speed of sound around both of you, or in the entire region, or so in that particular region in the what, in the Grand Canyon. Okay, so the first thing we're going to do, is what, is calculate the speed, which is going to be the speed of sound, using temperature. So that's straightforward, done like this. So let me just zoom out a little bit. Yeah, so VS, I'm going to do it in one line. VS equals 331, let me zoom in, 331.4 plus 0.606 times 35. Bedmass says I need to do this one first, and I will. So 331.4 plus, and let's do this quick, 0.606 times 35. That is 2121, which means the final answer for the speed of sound in the Grand Canyon in that region at that temperature is 352.61 meters per second. Okay, everyone? 352.61 meters per second. Does that answer make sense? Of course it does. For why? Because the temperature is higher than zero. Remember, the temperature is higher than zero, which means your speed is higher than 331.4 meters per second, because that was the speed at zero temperature. Okay, at 0 Celsius temperature. Okay, so that's the first step. Okay, I'm hoping it makes sense so far. The second step, everyone, the second step. Now, okay, everyone, listen carefully. Even though we're dealing with sound, listen carefully. Even though we're dealing with sound, we are still dealing with what? We're still dealing with the speed of sound. We're dealing with the speed of sound. Remember, speed is speed. It doesn't matter in what context it is. You still have to think of it somehow, sometimes, using kinematics back from what? From unit one. What I'm trying to say is, even if you're dealing with complicated sound waves, you're still dealing with what? Speed, which is distance over time. Okay? Now let's think about this for a second. In this question, we just calculated the speed. So mentally, check mark on speed. Number two, we also know the full time. That the wave took to travel from you to the rock back to your friend. I'm going to say it again. From you to the rock to your friend. Okay? So think about it. We have speed, we have time. If you have speed and time, what can you calculate for sure 100%? Anyone? Yes, Haley, go ahead.
Distance.
Absolutely. Yes. Even though this is waves and sound and fancy stuff, nope. Bring it down to simple basic concepts. We can definitely now the full distance, as Haley perfectly said, traveled by sound all the way from you to the rock, back to what? Back to your friend. So we can call it distance. I don't care if you call it delta D or D at this point. Just call it something representative. So I'm going to call it delta D. Fine. So equals what? Equals speed multiplied by time, which is basically, remember the triangle, everyone. I'm basically doing the famous triangle of D, V, T, but because I have V and I have T, I'm going to multiply them together. Okay, so right now, I'm going to multiply the speed of sound, 352, and I'm keeping all of my digits because I am in the intermediate steps right now, times zero point 0.7. Okay, so how much is that? Oh, it's already here, times 0 0.7. So 246, I'm going to say 83. 246, is it 246? Yep, 246.8383. Is this in meters per second or meters? Is this number in meters per second or meters? Anyone? This number right here. Yes, let's go with Haley.
Meters?
Absolutely. Because, and Layla, I'm assuming you were saying the same thing?
Yeah.
Yes, obviously you remember you already had speed. You cannot get another speed. And you just called it distance as well. All right, so this one is meters. So meters. Okay. I hope so far things are making sense. By the way, you should know that so far we really haven't touched the problem itself because we are just calculating things. We're kind of like going around the hard stuff. Okay, we calculated the easy thing first. It was the speed because we have the temperature, and then we went back to what? And then we went back to kinematics to calculate the distance. Now we're actually gonna do what? The most important and kind of like the last step in the problem. Okay, everyone, check this out. I want you just to focus here. Sound traveled. So we call this X, right? We call this X. We call this distance X. Forget question mark. Let's just call it X. So everyone, think about it this way. The way that sound traveled, was this way first. Just imagine this way first, and then this way after. But if you really think about it, the second one I sketched is actually this one back and then plus this one. Okay, so why am I sketching it in such a broken down way? Because now you know that, everyone, think about it. The full distance that the sound traveled is actually, look at me, X plus another X plus another 20. So think about it. The sound traveled X first, and then technically, before it reached your friend back, it had to reach you back, which means it had to go another X backward, and then it needed to what? To pile up the extra 20 until it got to your friend behind you. Okay, so really, there's an X here, there's an X here, and there's a 20 here. Okay, X, X, and 20. Okay, so Wadah, yes, go ahead, sorry. Wadah, you have your hand up. Sorry, I just saw it. Okay, maybe it was by
So
mistake.
subtract the 20 and you divide it by 2.
Okay, so exact. So the best way to actually do this now, I'm gonna take out this circle right here, is to really just write the what? Just write the equation for it. So we know now that this distance right here, everyone, this distance, let me just zoom out. Come on. Zoom out. This distance right here is what? Is X plus 20. X plus X plus 20. Why? Because that's the whole time of 0.7 that it took to travel. Okay, it's not just this part or this part or this part, it's the whole thing. So that means what we're gonna do now is say that 246.83 is equal to X plus X plus 20. Okay. And now no more physics is there. All we have to do now, I'm just going to do the rest here. So I'm actually going to do it right here. All we have to do now is just solve the equation. Solve the equation. 246, 246.83 equals x plus 20. Well, what do we do first? We clean this up. So x plus x squared plus 20 equals here 246.83. Can someone tell me what to do now? How do I solve this equation? Who's got their hand up? Waddah, Layla, and one more. Who's the one more? Open queue. Sorry.
So Ramadan, why do we have an x squared?
Because it's x plus x.
Isn't that 2x?
Yes! I was waiting for someone to say that. Remember, even online, I'm still going to make those purpose mistakes. Yes, thank you. Remember, everyone, x plus x plus x plus x plus x is 5 x's, not x to the 5. Remember, when you add or subtract, you just get more of the same thing. You do not get a higher power. You only get higher or lower powers when you multiply. When you multiply, you get higher powers. When you divide, you get lower powers. Yes. Okay. Perfect. Thank you. I was waiting for someone to say that. So obviously, it's not 2x. X squared. It is 2. Where is it? Oh, sorry. Eraser tools. Yes. There we go. Thank you. So it's 2x plus 20. And now it's almost back to the what? To the same way. We have got to migrate the 20 back to the other side. Remember, numbers go with numbers. So 246.83 minus 20, still equaling 2 x's. Subtracting gets you 226.83 equaling 2 x's. And that gives you x equals 226.83 divided by 2, which is 113. Half of 83 is 42 meters. That is how far you are from the what? From the rock formation. And that's the only way that's you screaming from you to the rock formation back to your friend at the temperature of 35 degrees Celsius is going to take exactly 0.7 seconds to travel from you to the rock formation back to your friend. Obviously, the sig fig situation needs to be dealt with. 35 is 2 sig figs. 0.7 is sadly 1 sig fig. 20 is a disastrous 1 sig fig. I know, shouldn't have done that. So let's say we're going to change everything to 3 sig figs. So everyone, I'm going to go here. I'm going to make this 20.0. That's 3 sig figs. And this 0.700, that's 3 sig figs. And 35, 0, 3 sig figs. So now we are good with what? With 3 sig figs here, which is 113 meters of distance. Okay? 113 meters per distance. Yes. By the way, this is a very common problem in sound physics or echo physics, where you have to actually basically use the sound speed with temperature and then kinematics with the triangle dVt, and then just basic logic into knowing that I traveled 3 distances, an x forward, an x backward, and an extra 20 back. Okay, so I hope this question related a lot of things in a sensible way. Hopefully you can watch the video again. And by the way, there will be a problem like this in the waves and sound test. By the way, I could have done the other way. I could have given you the distance between you and the rock formation and asked you for distance between you and your friend. I could have given you both distances and asked you for the time. There are so many things I could ask you for because there are so many variables here. There's distance between you and the rock, distance between you and your friend. There's the temperature. There's the time. And there's the speed of sound. Okay, which honestly you will find once you know the temperature. Okay. All right. So I'm hoping this was a decent example. Complex, yes, it was meant to be. but good because it tied a lot of concepts together. Okay, another one. You drop a rock whenever they discover a well or a hole, they actually drop, and then they quickly see basically how long it took for it to produce the sound of it hitting the bottom of the well or the hole, and then they kind of estimate basically how deep that hole or that well is. Okay, so we're actually gonna do this problem now. So you drop a rock inside a 20-meter well. So in this case, actually, you do know how far it is gonna travel before it hits the ground, okay? Or not the ground really. You are on the ground when it hits actually the inside of the well. Okay, so you drop a rock inside of a 120-meter well, where the temperature inside of the entire well, all the way throughout the 120 meters down until the base or till the bottom, is 31 degrees. The question is simple. How long after you release are you going to hear the sound of the rock hitting the well's bottom, hitting the well's bottom? We definitely need the diagram here. I'm going to show you actually the easiest way to do the entire problem on the diagram here. Okay, so here's the diagram. I guess here's the ground, and here is the well. Here's the well, and there we go. Okay, all right. So what do we know about the well? Technically, we only know two things only. We only know two things. Number one, how deep it is. Well, I guess I could. Oops, sorry. Someone. Nope. Everything's good. All right. So I could put it here, but I'd rather actually put it on the side, and you will know why. Okay. So I'm gonna put it here. So 120 is this distance. 120 meters. Okay. Got one number in. The other number is 31 degrees. 31 degrees. That I'm going to put right here in the middle. 31 degrees Celsius. Sorry, 31 degrees Celsius. Okay. So the question now is, what happened? What happened? Well, everyone, look at me here. So the beginning is you were holding the rock. The rock was not moving. And then you did not drop it. Sorry, you did not push it down. You released it. You let go. You gave it zero speed. It was zero, and the moment you left it, it was zero speed. So right here, we're gonna say that this is the side you were holding the rock here. This is the side you're holding the rock. So initially, you were holding the rock. That's the hand. Sorry. You were holding the rock. Okay. So initially, the rock was not moving. So now I'm gonna take out the hand. I'm gonna put my vibration lines, as you all know, those lines right here. Okay. Initially, it was not moving. And then you let go. So obviously, what's going to happen? First, the rock is going to move down. Move down. In a what fashion? In an accelerating fashion. So now you are getting basically the message that we're going to have to do some acceleration in this problem. Yes, told you before, physics is all connected. And the more complex it gets, the more connected it gets. But at least now we're just connecting it to one simple field we did before, a simple topic, which is what? Which is kinematics, okay? So at least I know that at the end, right here, it will reach the ground with a certain amount of speed. By the way, I don't need to know the speed. We just need to know that it is gonna reach it with some speed, okay? Now what's gonna happen? By the way, everyone, just so you know, do you think you're going to hear any sound during this trip? Who's got an answer for that? Yes, Leila?
No.
Okay, Wadah, what's up?
Isn't like the only force on the rock is like gravitation?
It's gravity. It's still it's still near the ground surface, so it's gravity, okay? Okay, so obviously, everyone, there is no sound made because when you drop it, you're still not hearing the sound. Okay, so no sound yet. The sound is only gonna be made when right here, when it hits the what? When it hits this ground right here. So you know that when it hits, sound is gonna travel up very fast. So I'm gonna sketch now the second trip that's interesting, which is the sound traveling. Obviously, you know that the sound is traveling everywhere. So it's here and everywhere. But I'm just making my diagram simple by leaving one side for the accelerating motion and one side for the what? For the, for the, what do you call it? For the sound motion. Okay, so let me just take these out. There we go. Okay, so we know that sound is going to travel only in the second trip. So we have only two trips here. We have an accelerating trip that has nothing to do with sound, and we have a sound trip that has nothing to do with acceleration. Literally, this is two distinct problems completely treated separately from each other. So let's do the first trip, okay? The first trip, everyone, the first trip has nothing to do, one second. Yes, the first trip has nothing to do, absolutely nothing to do with sound, because it's just a trip of an object kinematically speeding up all the way down. So this is just what? This is just kinematics. What's the initial speed of the rock? 0. Yes, Haley said 0, and she's right. So VI equals 0 meters per second. Distance we are given, it will travel 120 meters into the ground. 120 meters, no meters per second, just meters into the ground. Okay, we got two numbers. Remember, kinematics work with three numbers at least, or always three. What is the third number that is there, but it's not told explicitly to you? Yes, Wadah, you wrote it right, but you said meters per second. Can anyone else tell me what it should, 9.8 should be? Yes, exactly. Avery said it. 9.8 meters per second squared. Remember, we already have a speed. We just need the acceleration as it goes down. So A is equal to what? 9.8 meters per second squared. Okay, good. So let's recap. VI we know, delta D we know, A we know. There are two things we don't know. We don't know the time, and we don't know the final speed of hitting. Okay, which one of those things is important to us here? Only the time. I mean, we could calculate how much speed it has immediately before it hits the ground, or the bottom of the well, I should say. But for absolutely no reason is that important to us. The only thing that's important to us to know for this particular problem is the delta t of traveling this trip. So delta t equals question mark, question mark, question mark. So basically now the question is, which part of the toolbox, by toolbox I mean the big 5 kinematic equations, is the one we need to use? Do we need to use equation 1, equation 2, equation 3, equation 4, or equation 5? Well, we need to use the equation that does not care about VF. We need to use the equation that does not care or does not have VF, final speed, VF in it. And the only equation that has no VF in it is equation number 3. Equation number 3. Equation number 3 is the following. I'm going to write a different color. I'm going to make it just... equation number 3 is... I'm going to actually put it right here. So file, new, save. Delta D equals VI delta T plus 1/2 A delta T squared. Okay. Well, the good news, actually, you know what? I'll also write it here, but I'm just going to make my 120 here, right here, 120 meters. Okay. So delta D equals VI delta T plus 1/2 A delta T squared. Then let me zoom in. So what's the good news, everyone? What is the good news about VI? Well, VI happens to be a perfect 0. Remember, VI is a perfect 0. What does that mean? It means that this is going to be completely zeroed out. This whole thing is going to be zero. I know some of you might say, but I don't know the delta t yet. You don't need to know the delta t to say it's 0. Remember, 0 times anything is 0, even if you don't know that other thing. No matter what value delta t has, big, small, anything, the VI of 0 will completely kill that part of the what? Of the expression, of the equation. Okay, so now we have a smaller and easier equation to deal with. It is delta D equals just 1/2 a delta t squared. Okay, I'll plug in some numbers if you like. Let's actually do it with numbers this time. So this will be 120. This will be 1/2. This will be 9.8. And this will be delta t squared. Okay, clean up. 120 equals half of 9.8 is an exact 4.9 delta t squared. Should I divide or should I square root first? What do I always do first? Yes, divide. Always clean up. The square rooting or exponents should always wait until the end when you are solving, not when you're plugging in when you're solving, like reverse BEDMAS. So delta t squared is 120 slash 4.9. Well, how much is that? Well, let's see. There we go. 120 divided by 4.9. Oops. 120 divided by 4.9. 24.49. Yeah, very close to 25. Which means delta t is the positive square root, because time could never be negative. More of a math comment, but still valid. I'm going to take the square root of this guy. 4.948, which is 4.95. 4.95 seconds. So now we know what, everyone? Now we know that, one second. Now we know that it took, by the way, this is only 50% of the whole trip, because we know now it took only 4.95 seconds just for the rock to drop. No sound has been produced yet. Okay. Well, now I'm going to reverse, or sorry, get my attention to this side of the problem, which is basically what the sound side. So the sound side, I have the temperature right there. I can calculate the speed. So Vs equals 331.4 plus 0.606 times 31 degrees, which is 331.4 plus, I don't know what that is, 0.606 times 31 degrees, 18,786. Add those, you get, you get plus 331.4. You get 350. I'm going to say 19 meters per second. So that's, everyone, that's the speed of sound. Listen up, everyone. This is the speed of sound in the well, regardless if there's a rock being dropped or not. If there's a sound made in the well, it will travel up, down, right, left, diagonal, whatever, in three-dimensional space. It will travel the air will vibrate in a way to make the sound wave travel at 350.19 meters per second. It doesn't matter who produces the sound or what kind of an object produces the sound. We have the speed. We do have the distance, because guess what? This side of the well is also 120 meters deep. 120 meters deep. So guess what? It's back again to the what? To the triangle of kinematics, dVt. So I can now, or now we can find that delta t for the second trip, or for the sound trip, is 120 divided by 350.19, which, by the way, we expect it to be a very short time. Think about it. If you're traveling 120 meters at a speed of about 360 meters per second, yeah, you're going to get that in 1/3 of a second. You're very fast. Okay. So if we divide 120 divided by 350.19, we get 0.3426 or 343. So 0.343 seconds. So now what do we do with both of those times? Remember, because we want the full time from the moment you dropped till the moment you heard the sound. What do you do with those two values? You perfectly add them up, because remember, when it was going down the rock, you did not hear a thing. So you still had to wait that time. And then you also did not hear anything as the wave was going up. You do not hear it until it hits your eardrum, which means 2 times had to pass before you actually heard. It's the time that the rock dropped, and then the time that the wave raced all the way up to your ear. So that means finally the delta T, I know you want to call it delta T total if you want, is what is 4.95 plus 0.343. That is 4.95 plus 0.343. 5.29, 5.29 seconds. I believe the sig fig situation is 2. This is 2 sig figs, and this is 2 sig figs. So that means this whole thing should be 2 sig figs, or 5.3 seconds. 5.3 seconds. Okay, everyone? By the way, usually it's the reverse problem that happens. You do not know how deep the well is and you want to calculate the time. No, you actually calculate the time. Sorry, you measure the time and then you do the reverse calculation to what? To find out how, what do you call it? How deep the well is. Or maybe you're interested in knowing how much the air temperature is. Maybe you don't have a thermometer on you to actually measure the temperature. So you're going to do it reversed with what? With estimating the speed of sound and so on. I'm just trying to show you that basically all of these things are somehow connected at the end.